right, hi everybody. I'm just going to give it about 5 or 6 minutes, see if anyone else shows up while I get set up. So if you're watching the recording, skip to 5 or 6 minutes into the video and then we'll get started. At least I look super cool with my headset. What's that? It started, I'm just waiting to see if anyone joins online or if anyone comes in. There's only one guy who comes in, but I'm just making sure that no one's just trying to join the meeting on the Zoom. Yeah. So I give them 5 minutes or so before I actually start, which means everyone who's watching the recording has to skip and try to figure out when I actually start. But that's all right. If I was really keen and really good at this stuff, I would find a way to like cut out the 5 minutes, but I haven't figured that out yet. So one day. Okay, guys, looks like it's just going to be me today, so no one's going to be here live. If you're catching the recording, keep in mind that if I'm talking rather quickly, it's because I'm here talking to myself. Feel free to use your pause, rewind, and replay functions as much as you need throughout this. I think today will be slightly less tricky than some of the last days have been. We're going to talk about ratios, proportion, and scale. And we're also going to relate some of these things to the triangle type problems we worked with the last couple days. You'll notice that pretty much all of this course has had to do with triangles, and that's because in carpentry you work with triangles all over the place. Framing a roof, framing a deck, or otherwise, it's all sort of works through the same ideas. So to get started, I want to really quickly talk about ratios. Ratios are something we probably have heard of and talked about before. You know, we talk about the ratio of filling to cookie in an Oreo cookie. It's just an amount of one thing to an amount of another thing. And we typically refer to them as fractions. So for example, we might have a bag of cement that needs to be mixed at a ratio of 3 parts water to 3 parts cement to 1 part water, right? We have 3 cubes of cement that are the same volume as our 1 cube of water, giving us a 3-to-1 ratio. We can write ratios in different ways. Sometimes we'll have 3-to-1. Sometimes it'll be written 3 as a word to 1. And then sometimes you'll get like a 1/3 ratio. They'll say there's 1/3 the amount of water as cement, but that gets a little confusing. We're going to stick primarily to these two ways of writing. Some others might come up as we go, and I'll make sure to point those out if they do. So ratios, I think, are pretty simple. It's something we're all kind of used to thinking of and talking about, but we need to make sure we have some background on them before we start talking about proportion. Proportion is a way of relating to ratios. So for example, if I have the same mixture of cement, I need 3 parts of cement to 1 part water, and I want to use 9 parts of cement. I need to have a way of figuring out how many parts of water I need to use. So we do that by equating two fractions. In the example I just gave, let's say that A is 3 cement and B is 1 water. Now this is equal to something, some other fraction. We use this equal to say it's a proportional relationship. So those two things are locked in step. So with the example where I have 9 bags of cement or 9 parts of cement, go away, I know I'm muted. This happens every time, and I yell at the screen for a few minutes. We're back. So if I have 9 parts of cement, the top of my fraction now is 9 cement and something of water. That is what we want to find out. So because we know we want the same ratio of cement to water on the left side and the right side of this equal sign, we can solve this equation using our cross multiplication and division that we talked about briefly the other day. So remember, cross multiplying, we take the top number we have that's across from a bottom number. Why is that moving and not writing? I think my green pen is broken. I had that problem yesterday. We take the top number that is across from a bottom number on an angle just like that, and we multiply them together. So 1 times 9. Then we divide by the last number we have left. In this case, it's a 3. So divide 3. 1 times 9, I think we can all do in our head, but let's pull up a calculator and make sure. 1 by 9 equals 9. Great. And if we divide 9 by 3, we get 3 equals 3. So how many parts of water do we need if we want to use 9 parts of cement? 3. 3 parts of water. Okay, so these proportional, I'm going to have to calibrate my board in just a sec, but these types of relationships are going to come up all the time. Mixing cement's a great example, particularly if you're going into carpentry. Everything you build needs a base, and you'll be using that quite a lot, but we can extend it to other problems as well. we're going to start with some word problems today. We're going to skip right past all the nitty-gritty, just pure math stuff. So I'm going to do a quick calibration of my board. So this will just take a minute, and hopefully it will be playing nicer with me after this. I can't say I love the smart board, but for the format of this class, it works quite well. All right, so our first example, talking about proportion and ratios, is at East Middle School, there are 58 left-handed students and 609 right-handed students. So we could say, we could write this as a fraction, we could say there's 58 left-handed and 608 right-handed. Or better yet, actually, I'm going to change my mind on that. I said earlier fractions aren't the best way. Let's write this as a ratio. 58 to 609. Okay. If the number of right-handed and left-handed students at the West Middle School is proportional to those at East Middle School, that means that the fraction created by those numbers is equal. And the West Middle School has 45 left-handed students. How many right-handed students are at West Middle School? So this is really, really wordy. This is a pain in the butt, but all we have to do is remember that proportionality, if it's the same proportion of left-handed people to right-handed people at one school to the other, then the fraction of left-handed people divided by right-handed people must be equal at both. So the one we know is that East Middle School has 58 divide 609. So 58 right, sorry, that's 58 left. 58 of the students at the East Middle School are left-handed, and 609 are right-handed. This is equal to or proportional to those numbers at West Middle School, and at West Middle School we are told that 45 students are left-handed. Left-handed are on the top for East Middle School. We're going to keep them on the top for the West Middle School. So 45 students are left-handed, and some number of students we want to find out are right-handed. How do we do this? Again, we cross multiply and divide. We take the two numbers we have on an angle, 45 and 609, and we multiply those and we divide by the remainder. Okay, so pull out a calculator. Nice and easy, clear everything that was there. First step for any calculation. We go 45 multiplied by 609 is equal to 27,405, and we divide 58. 472.5. So in this example, we can't really have decimal places. We can't have half a person. If we did, it would be weird and a little suspicious. So we're going to round this to the nearest whole number. Fives always round up to the next number, not down to the number that you have. So we're going to say that there are 473 right-handed people at West Middle School. So I hope that you guys are able to follow along so far. Hey, Aaron, come on in. I hope you guys have been able to follow along so far. Remember, I'm recording without anyone. I've actually got someone just coming in now. If you need to, please pause, rewind, and use your replay functions as required. There will also be a worksheet associated with this lesson that you can work through and contact me if you have any questions as you go. That's all right. So for our person just joining us, we're talking about ratios and proportions. Ratios are things like amount of filling to cookie in an Oreo cookie, how much cement to water you need to mix the right mixture. Okay. Oh, yeah. Yeah, there you go. Filling of a donut to the amount of bread. And proportions are just ratios that have to be equal to each other. So if you have a 3-to-1 mixture, cement to water, and you want to use 9 parts cement, how much water do you need? Okay. So this is the second example talking about proportion. And it tells us the table below shows us how much red and yellow dye is needed to mix a particular shade of orange. So like if you're mixing up paints at a paint shop, and how much yellow paint would be need to be used if you only had 3 milliliters of red dye. So you'll notice in this chart that all of our ratios of red and yellow dye have more than 3 millimeters of red dye. So if we want that particular shade of orange and we want to use only 3 milliliters of red dye, we're going to have to do some math to figure out how much yellow to use. Now, this question, what it's done is given us a bit of a red herring. It's given us 3 different ratios, but we only need 1. If all of these give us the same exact orange color, then all of these are going to be the same ratio. We can check that. Let's say red dye divided by yellow dye is our ratio. So 10.5 divide 28 should be equal to 7.5 divide 20, which also should be equal to 9 divide 24. Is that right? Yeah. So let's check that. Pull up a calculator, move it over so we can see everything on the screen. Clear whatever's there. We're going to go 9 divide 24 equals 0.375. So hopefully that's the case for all of these. 7.5 divide 28. Uh-oh. Maybe this isn't a good question. Table below shows how much red dye and yellow dye is needed to mix a particular shade of orange. How much yellow paint would need to be used if you have 3 milliliters of red dye? So these ratios should be the same. If they're not the same, then you don't get the same mixture of orange. So let's change this question slightly. This is my bad. I didn't pay close enough attention as I was building these problems. So let's ignore these two. And let's just say that the question says we need 9 milliliters of red dye to prepare 24 milliliters of yellow dye to prepare the particular shade of orange. And we only have 3 milliliters of red dye. So that is a 9 to 24 ratio of red to yellow. And we need to match that where we have 3 milliliters red. So let's make a fraction. Let's go 9 red divides 24 yellow. And this should be equal to whatever amount of red dye we do have, 3 red, divide by some amount of yellow. Sorry? You've divided 9 by 24? Yeah. So 0.375 is what our 3 divided by something has to be equal to, right? Once we have this equality with 2 fractions where there's 1 missing value, what do? Just like yesterday, we cross multiply. We take the 2 numbers we know on the diagonal and multiply them, and we divide by the last number we have left. So 24 times 3 is 72. Divide 9 is 72 divide 9. Can't do that in my head. 8. I knew it was nice. For those of you watching online, I'll type in on the calculator there. 72. Oh, I hit the wrong number. I hit 72 divide 8, got 9. So 72 divide 9 equals 8. You're right. This guy in the audience is kicking my butt with his calculator skills. In any case, the amount of yellow we need was 8 milliliters to make that particular shade of orange. Apologies that this example doesn't actually make any sense. Don't know how that happened. Moving swiftly on though. The next thing I wanted to talk about today was scale. Scale is just the length of a drawing or model or anything really compared to the real thing that it represents. So we'll talk about this in model cars, maps, blueprints of houses will often be drawn to scale. And it just means exactly that. It's a ratio and it represents the size of the drawing to the size of the real thing. So as an example, if someone named Jason has a map of BC and they want to know the scale of the map, they use a ruler to measure the distance from Victoria to Vancouver on the map, and they find that it's 7 centimeters apart. So on the map, V to V is equal to 7 centimeters. This person happens to actually know, just off the top of their head apparently, that Victoria and Vancouver are 93 kilometers apart. So actual V to V is equal to 93 kilometers. So what is the scale of this particular map? Well, we said that the scale was the size of the thing on the map, 7 centimeters, divided by the size of the thing in real life, 93 kilometers. Now, we're going to immediately notice an issue here, and this is to do with units. These two units are not the same, so they don't mix. If we want to do math with these two numbers, we first have to put them in the same units. We can recall from previous days that we can do that with either one of these. I'm going to convert 93 kilometers into centimeters, just totally arbitrarily. I could have converted the 7 centimeters into kilometers and get essentially the same answer. But let's do the 93 kilometers to centimeters. So we're going to go 93 kilometers. We're going to multiply by 1 such that we can cancel out the kilometers as units. We know there are 1 kilometer for 1,000 meters. And we're not quite there yet. We still have to convert from meters to centimeters. So in 1 meter, there is 100 centimeters. And this is equal to something where kilometers and meters have canceled. And we've got a 93 kilometers written in only units of centimeters. So 93 kilometers, multiply 100. That's 1,000, not 100. And then we multiply all of that by 100 at the end to get 9.3 million centimeters in 93 kilometers. Fun fact of the day, this is exactly equal to 7 centimeters divided by 930,000 centimeters. You'll notice once we get these in the same units that the units can cancel, and then we're just going to be left with a number, and that number represents the scale. So we can type this in. I'm holding the pen. Can't be holding a pen. Gotta love smartboards. Stop it. Technical difficulties, as always. I think we're getting better though. So 7 centimeters divide by the 9.3 million is equal to 7.52 times 10 to the negative 7. You see this little e here in the calculator? That e is a times 10 to the negative 7. That is a scientific notation. It's a way we use to write really, really big numbers and really, really small numbers without having to write 0.000000. All this means is that the decimal place was moved 7 times. So if I was to write this number without scientific notation, it would be 0. We move 7, so 0.000007 ... and then all those numbers. But that's a pain to write. So what we write instead is we say that it is 7.53 if I round correctly. So I'll do that by 10 to the negative 7. Okay, so we can write scale like this. We can say that the scale is 7.53 times 10 to the negative 7, the actual size, or we can say that the scale is 7 to 9.3 million, and potentially, if we're lucky, oh, what did I do? If 93 divides by 7, it does not. So we can't simplify this anymore. If 93 divided by 7, I could have written this maybe as 1 to some number, but in this case, it doesn't work out quite that nice for us. I would prefer to have scale written as this, the 7 to 9.3 million, rather than just a number, but it's equally correct and you can still work through problems in the exact same way. So, somebody named Trish wants to build a scale model of their favorite car, the Tesla Model X. The real car is 5.04 meters long, and they want their model to be accurate at 1/10 scale. How long should their finished model be? So, we know that the scale is 1 to 10, and we know that we often represent scales as fractions, 1/10. And if something is at a particular scale, then there's a proportionality between that size of the thing you've made and the real thing and the scale it's written at. So 1/10, the scale that we want to make the car at, has to be equal to the size of the model. So size model divided by the length of the real car, 5.04 meters. Okay. Now we've got exactly the same thing. We've got two fractions where we don't know one value. So what do? We cross multiply, two numbers on an angle get multiplied, and we divide by the last number that we have. In this case, we're going to go clear everything. I'm going to erase that little red line. 1 multiplied 5.04 is just 5.04. And then we divide by our last number, which is 10. 0.504. So the scale model, the size of the model, or the length of the model rather, should be 0.504 what? 0.504 meters, right? It has to be meters, and it has to be meters because this was in meters, and this side of the equation was unitless. It's just a fraction, it's just a number, okay? Right, so if this side is just a number, and this side is equal to it, it has to be also just a number, right? And we know there's meters on the bottom, so there has to be meters on the top so we can cancel it out, right? If it wasn't meters on the top, then we would have something with units equals something without units, and that doesn't make sense. So you can see how these problems, once you wrap your head around it, are very simple. There's very little math. Write out your proportionality, cross multiply and divide, and you're done. But they're really weird to wrap your head around, okay? So this is just going to take time and practice, going through those practice worksheet questions, making sure you contact me if you need any help as you work through those. This leads us nicely into something we often talk about called similar triangles. We've been talking about ways to solve and figure out the lengths of sides of different triangles this whole time, but we haven't touched on the concept of similar triangles. And similar triangles are just sets of triangles that have the same internal angles. When we have sets of triangles with the same internal angles, we can say that their side lengths are proportional to each other, okay? For any triangle, we can take two of its sides and we can write them as a ratio. As an example, we could say that this vertical side to this horizontal side has a ratio of 3 to 4, okay? We could also say that this vertical side to that horizontal side has a ratio of 6 to 8. Now, these triangles drawn here don't have side lengths labeled, but they are in fact similar triangles, or sorry, they don't have angles labeled. I know I defined similar triangles up here by saying they might have different side lengths, but they have the same internal angles. So how can I confirm that these are the same internal angles? Well, I said a minute ago, if you have similar triangles, their side lengths must be proportional. The ratio of their side lengths must be proportional. That means 3 divided by 4 must be equal to 6 divided by 8. Okay, can we see if this is true? Hell yeah, we can. 3 divide 4, 0.75. 6 divide 8, 0.75. Right? So when you have similar triangles, if you either you know their internal angles, all three of them, I can actually tell you this is 30 degrees and this is 60 degrees and this is also 30 degrees and 60 degrees. If we know those internal angles are all the same, then we know this proportionality will be true, and we can use that to solve for different sides of one triangle if we don't have all of them. An example of that I think I have coming up just now. So here we go. There's two triangles here, and we can tell that they're similar triangles in this case because they share one angle here, so that angle we know is the same for both of them. And these lines are extensions of each other, and this line is parallel to that line. Okay, so if, now we're getting into a bit of geometry that we don't have a lot of time to spend on because of the nature of this being a crash course, but suffice to say, whenever you have one of these triangles where there's one triangle, they share an angle, and the sides just get extended, and then whatever connects those sides later is parallel to the original, then you can guarantee yourself through a whole bunch of different geometry rules that this angle is going to be the same as that angle, and that this angle is going to be the same as that angle. Okay, we can also kind of convince ourselves that this makes some sense just by looking at the diagram. It just looks like they're about the same. But to be more mathematically rigorous would take a bit more time than I think we have for this program. So in this case, we have two similar triangles, and we want to know this x value right here. Now, this x is actually kind of a weird one. It's asking for this length right here and not the whole side length of the triangle. But we're going to start by finding the whole side length. Just for anyone who's online that may be confused, yeah, the green pen's broken, that's frustrating, that may be missing where exactly the two triangles I'm talking about are. I'm talking about this triangle here that I've drawn in blue and this triangle here that I'm going to dot in red because they take the same space. Okay, those are our similar triangles. So we can take a ratio of side lengths of either one of them and set it equal to a ratio of the same side lengths for the other, if they're similar triangles. The blue triangle, we know two sides. So let's take this side to this side as a ratio. That is a ratio of 7 to 15. And that should be equal then to the ratio in the red triangle of this side, the one that is mimicked by the 7, the 11. So 11 to something, whatever this distance is. We know those are proportional because these are similar triangles. They have the same internal angles. So we can set them equal. 7 divide 15 equals 11 divide the thing we don't know. We cross multiply and divide. So the two numbers that we have on the diagonal, 11 by 15, and then we divide by the 7. 11 multiply 15 equals 165 divided by the 7 equals 23.57 ... So this whole side length then is 23 point, I'm going to say 0.6 because it was 5.7, so we're going to round up. Then you just subtract 15 because we already know this length. This part of it is 15, so what's left with the x is 23.6 minus 15, which is equal 8.6. There's more digits, but we don't need them for this particular example. Okay, so again, this is, I think, fairly straightforward once you get into the math, but getting to the point where you really understand where to go at the beginning can take some time. It can take some understanding, and it's just a matter of doing lots of it. Once you start to do it a lot, it starts to become very intuitive. And then it's just a matter of setting up your fractions, cross multiply and divide, and you're done. I think we're actually making crazy good time today. So I think we're actually close to the end of today's. Let's see, do we have more? So here's one more. First question says, are these similar triangles? I wanted to talk a little bit about some geometry things. So we talked about it a little bit with this one where we said if you have one triangle that's like made up of a part of another, as long as that side that is not shared is parallel, those will be similar triangles. That will always be true. If they're sharing two sides and there's only one side that's different, if that side's parallel, you're good to go. This one uses another geometry fact, and that is when you have any two lines that cross each other, whatever the angle here is, as long as these lines are straight, will be the identical angle up here. Now, we can do some things to convince ourselves a little bit about this. So if I, can't use that pen, if I draw a horizontal line, we know that from, it makes an angle with itself of 180 degrees, exactly half a circle, right? So I'm going to pay attention then to 1/2 of this example. I'm going to only look at this angle and that angle right here for a sec, okay? So this angle is whatever it is, some angle, theta, we'll call it. And this angle has to be 180 minus that angle, because we know that this whole angle on the one line is 180, right? Half a circle. So now we have to figure out on the other side. Well, we know that these two lines are not, they're not curving, they're just straight lines. So if they're not curving, we can treat this just as a reflection over an axis. And when we think of it as just like kind of a mirror image, we can convince ourselves that those angles have to be the same, so long as the lines are not bent or curved in any way. The assumption we typically make when we look at these problems as a purely mathematical standpoint, if you're given a test in a drawing like this, you make the assumption that unless a line is clearly bent, it is straight. In real life, you wouldn't do this, but in real life, you would be able to convince yourself through environmental factors whether that line should be straight or not, right? So for this example, we can say, by that exact logic, that this angle and this angle have to be the same. So we've got one of our three angles the same. And we've also got labeled on here that this line and this line are parallel, okay? So if those two lines are parallel and they're creating angles with one line right here, I'll call that like that, theta 2, and one right here, theta 2. Again, you can see that's just a mirror reflection. Even though these triangles are different sizes, so there's a scale factor happening, but it's just a mirror reflection flipping over an axis. Same thing right here. So I can call this theta 3 and theta 3, right? Just a mirror reflection over that axis. So we have three angles that are all the same. We have similar triangles. So we can use proportionalities to solve them. This is kind of a difficult question because everything is mirrored and flipped around. So we're looking for side length A and side length B. I'm going to suggest that we start with side length B. The trick to this will be figuring out what side on the smaller triangle or the top triangle corresponds to side B on the bottom triangle. We have theta 3 here and theta 2 here. And in this picture up top, we have theta 3 on this side, and I accidentally erased it, but we have theta 2 on that side. We want the side connected to theta 3. So that is this 2 centimeter side. Okay, it's very tempting to say that it's this side labeled A because you go, oh, the two triangles and we want the side that's on the left, but they've flipped around on an axis. And so we have to be really careful about how we determine which side corresponds to which, excuse me, other side. Hiccups today. So we know, this is a difficult question actually, okay. So what sides do we know? Well, we know lots of proportionalities. Let's start writing one we know. We know that B over, let's say the ratio of this side to the ratio of this side, two sides we know on the bottom triangle, or know or want, okay, is equal to 7.5. So B over 7.5 has to be equal to the fraction of the same corresponding sides on the other triangle, which is going to be, B we said was related to 2 over, now this 7.5 relates to A. Theta 2 and theta 2 are up here, so that's over A. So we have two unknowns. So we can't actually cross multiply and divide just yet, okay? But what if we found another set of ratios or another proportionality that we know? Let's look at the top triangle. We know two sides on it, right? So let's take the horizontal side, the very, very top side, 3, and then we'll go to the side next to theta 2, which is 2 centimeters, over 2. This has to be equal to this bottom side. That corresponds to the 3 centimeter side. I'll call it X because we don't know it. And we'll divide that by the side corresponding to 2. 2 is the same as B, which is, yes, it's the same as B, right? Do I have another question that doesn't make sense? I might have another one that's, this is probably more difficult than I wanted it to be. I think we can get through it. So 3 over 2, unless I'm making a mistake in which sides are related. So the 3 is definitely related to X. The 2, yeah, is definitely the same side as B. Or do we not have enough information? This is our last example today. Oh, this is our last example today, I'm pretty sure anyway, so we can always cut it short if we really need to, because we have gotten through probably more than enough, but now that I've started this, I really would like to figure it out. 3 over 2 is those proportional to X. Yeah, I'm gonna actually stop the recording here. So sorry, I will try to make sure if I come up with a solution for this one, I'll let you guys know. But it's beyond what I think is fair to ask you guys in the context of this crash course style program. If we had 2 months, I'd be giving you questions like this, but I'm going to skip this one for the purposes of this recording. So I'm going to just end this stream and then take the rest of this offline with those people that are here.